what they are. The basic principles of contemporary physics one of the principles is that everything, if you were to know everything about state of universe at present time, everything, then you will be able to predict future perfectly. If it is wave function that you calculate wave function of a future universe. But this is not the case for systems with memory. So if we have certain state for systems with memory, then what happens next depends on the whole history of the system. Let's say you were offered to create basic laws of universe so that it is pushed and evolves somehow. What would you prefer? To just to give strict laws to the universe so it will evolve. And then in principle everything is predictable. Everything is known. Or another possibility is to give a chance to have some feedback. So it evolves somehow, it finds that it's a wrong path. So go back, correct, and do it again, but this time different way. So it's not simply memory, it's also some kind of feedback, but you need memory.
So like what sort of goal would it be for?
I don't know. Did you just you see, would it be known? Probably it would be already reached somewhere. This is the beauty that we don't know what it would be. No, this is too general. We will actually this is not this is too general, but if we investigate simple models of systems with memory and find that behavior of this system, those systems, is somehow different from behavior fundamentally different. There is something that the systems with memory don't have. So if we find this difference, then we look for evidences of presence of memory in system. Who knows? Could be the universe has some kind of memory. What is in how humans and societies would appear and have memory and their purposes if basic properties of matter didn't have it. This is kind of philosophical problem, but it makes sense to investigate again simplest systems with memory and to see what we can find. Let's define. We are mathematicians, and Quran, there should be some mathematics, not only general study. So mathematically, a system of memory can be defined in this simple way. So new state, and X is a set of variables that describe any system with memory. So its state would depend on all previous states. This is a discrete system. In this case, n plus 1 states. N plus new value of state variables, they depend on all previous states. In principle, we will leave some room to consider systems which are continuous. And let's see what can we do. Again, this system, this description, is extremely general, and almost everything can be written like this, and you can obtain absolutely any properties. You cannot get some general properties of systems with memory from this equation. So, what people were doing, they investigated with simple systems. But what I will be talking about today is systems with powerful memory. And why powerful? Because there are many biological systems where powerful memory is simply a result of experiments. On the other hand, basic calculus of derivatives and integrals, where first derivative, second derivative, or n-fold integrals appear. It also can be naturally extended to fractional derivatives and integrals. And if we try to extend, many people try, famous mathematicians try. And they came to some models, but all of those models are models with memory. So derivatives become integral derivatives. And those systems, which described by fractional calculus, they also have powerful memory. So it's, in certain sense, it's natural to have this V power law. So, in this case, new value of variable depends on previous values, but there is a weight attached. And this weight is time passed since this moment, x, k, moment k. But this time to certain power. I write not alpha, but alpha minus 1, because when we make transition to continuous case, alpha will be the order of the fraction of the derivative. This is a basic model which we will investigate. Here we have n and k are indices, and their meaning is quite obvious. G is any function, and we will consider simplest cases when this G is sine or cosine, harmonic function, or G is a quadratic function. We consider non-linear. There are two sides to this talk. One is memory, the other is non-linear. But let's so alpha defines memory. K is a parameter. We allow us this system depend on certain parameters. And then we'll see what will have from use of this parameter. H, we want to consider a limit of continuous system. this case, x will be x function of time, which is continuous. And the values of xk are values of variables at time tk, which is defined by h time k. Quite important. So if we consider continuous system here, then we also want, there are some reasons for me not simply consider those values of variables and continuous time and the definition of tk, but also g to be of a certain form. And if I consider g of this form, then first of all I have to define what is this gamma. Gamma of alpha. Everything else here is clear except for gamma function. Now, do you know what factorial is? You know what everybody. Now, gamma function for integer arguments is defined as factorial. And you know, when we need old definitions in new spaces, we continue. For example, we had positive numbers, there was a need in negative numbers, we extended. There were there was need to calculate roots of from negative numbers. Appeared complex numbers. So we can extend this notion for fractional alpha, assuming this function will possess this property which is known for factorial. And there is almost unique, it's not unique, but almost unique way to define this gamma function. Then if we plug all those values here, we get the following sum. So far, is everything clear? Now, if everything is clear, then you also know integral calculus, because limit of this expression when h goes to 0 is exactly the definition of integral. And this is something that is called Riemann sum for the integral. So, okay, this formula for definition of gamma function. No, you see, it's not actually defined. You cannot calculate it still. For you need gamma function for a certain interval, for example, from 0 to 1. But there is. I won't go into in depth to this definition. But the gamma function is uniquely defined, and it is an extension to fractional numbers of factorial. There is integral formula which defines this function. So, you see, because it's a review, I won't go to details. At certain moments, you have to trust. Now, this is a Riemann sum for this function. And if we consider limit h goes to 0, then we have the following expression. And this is the definition of continuous system with memory. This is discrete system with memory, this is continuous system with memory. So now you know that this limit when h goes to 0, it's infinite. And for an arbitrary function, f of x, the integral is area. And this is function. And what we've done, we just divided into intervals which width is h, and then multiply value of function by h everywhere. And this is what we've done. You know what integral is. Okay, we define discrete and continuous systems. Now, by the way, if we go back a little bit, you see, when there is no this power, then we have simply, and here we have alpha equals to 1. Alpha equals to 1. So there is nothing here. We have that is equal to simply integral. This is integral. If alpha equals, let's say, 2, then that would be here a power -1, which is actually g times t minus tau. Negative power in denominator is the same as positive in numerator. And here we still have 1. But then it is known that this is actually double integral. So there is this property. This is double integral. Now, if we for fractional values of alpha, this is the definition of a fractional integral of the alpha. Alpha equals 1, it's just simply integral. Now, this is what I told you. It's a fascinating topic of fractional calculus. It's calculus of fractional order derivatives and integrals. It was born on September 13, 1695. And those names of Italian labels, they are well known for mathematicians. Leibniz was one of the founders of calculus, and he posed actually a question: what would be or answer to this question? What would be derivative of the order 1 half? Since that moment, many famous mathematicians worked on the development of fractional calculus. They had some ideas, what names. Again, they are not taught in high school, but they are famous. Who knows some of those names? You know. Whom do you know? Better?
Yeah.
Okay. And the definition of fractional integral, it comes from this property of n-fold integral. So if p is an integer, then this property is known. Then simply you may define integral of fractional order of this expression for fractional values. And the derivatives simply derivatives from this. You don't need to understand in depth, but we need some mathematics. Now, okay, those systems with memory, but motivation should come definitely not only from mathematics, but from outside. First of all, I told you this property of origin of memory with humans. But I also mentioned that many biological systems, they also possess powerful memory. And first of all, we'll start with humans. And simply in psychology, experiments show that human memory is failing as power law. So accuracy in memory task it is falling as power law. So we have power law memory. And also in learning, when you learn, you retrieve something from your memory and compare it. Again, this is a result that reduction in reaction times that comes with practice is a power function of number of training time. Then adaptation in biological systems, there are plenty of publications which show that adaptation also, they use power law adaptation to explain the behavior of biological systems on different levels, from even smaller than neurons. There's individual channels in, if you consider neurons, and let's see, this is an individual neuron, but from those small cells to the human as a whole. Now, you know that neurons are nerve cells. They receive information through those dendrites from other cells, and they send signals through axons to the other cells. And any neuron has multiple dendrites and only one axon. Now, in experiments, it was shown that the rate of firing of neurons, actually, firing, it's when neuron provides signal to the other neuron, to other cells. So when the rate of firing of neurons, it's a fractional derivative of slowly varying light potential. But we know that fractional derivatives are derivatives with powerful memory. It means that powerful memory is present at the very basic levels in humans, and not only in humans, in any biological system. Now, what is also interesting is that all our tissues in our bodies, in any like species, they possess viscoelastic properties. And those viscoelastic properties were demonstrated in all tissue organs. Brain, heart, liver, and even in bones, they are viscoelastic. They quite complicated polymer. They have quite complicated polymer structure. But behavior of such systems also can be described by fractional differential equation. I mean that their behavior depends not only on present state, but on history. So how will viscoelastic material react on external perturbation depends on history, and memory here is following. Why there should be fractional derivatives that correspond to probable memory? Because viscoelastic materials, they are somewhere between solids and viscous fluids. And in solids, stress and strain. So this is stress and strain. Displacement, force is proportional to displacement. It's Hooke's law, if you studied physics. And in viscous fluids, stress and strain are connected with this law. So here we have zero derivative, here we have first derivative. And in viscoelastic material, derivative will be of the order between 0 and 1. This is another application of powerful memory in our bodies. Rheology is a science that studies this kind of materials, and those materials are with memory.
So it seems like you're like, okay, so biological tissues correspond to reverse parallels, neurons correspond to reverse parallels, and all that. Can you give me an example of something that corresponds to like a different sort of memory, like not power one?
Not power.
Just because we did talk about that sort of thing, like existing.
No, I didn't think about that. Because my idea was to have power. But the first, actually, power law, systems with power law, memory, were discrete systems. The investigation has short history. Prior to that, systems with exponential memory were investigated. Where they appear, they were applied to relaxations in complex thermodynamic systems. There was principle, the result of that research was a principle of fading memory, meaning that whatever memory material is this influence of memory, it is fading with. Now, as I mentioned, there are two components important for this talk. First, memory, and the second is nonlinearity. The simplest law of dynamics, Newton's law, is Newton. So how a system will evolve depends on the source. And you remember, I already mentioned Hooke's law. So if we have Hooke's law, if we have a spring which will stretch, then this dependence is really dependence of force and correspondingly on displacement and correspondingly equation that describes systems which obey Hooke's law. But fundamental interactions, they're not linear. Gravitational law, it's 1 over r squared. Electromagnetic equations, they're also not linear. So most systems are not linear. The simplest systems that we will investigate will have the simplest nonlinearity. Here, this system has quadratic nonlinearity, and this system has simplest sign nonlinearity. This is called circle map. It's not general form of circle map. It's a particular form of circle map. And this map is called logistic map. And there are plenty of interesting things about those maps. For example, this map proposed by May in 1972 then was investigated by Mitchell Feigenbaum, and he received one of the highest mathematical prizes, the Wolf Prize for investigation of this map. He discovered universality in nonlinear dynamics. He discovered chaos in those systems and fast chaos, which is quite universal for all nonlinear systems. This is what he discovered. So this is logistic map, and for small values of x, if you start trajectory, it will converge to a certain point. But here, parameter is r. Who is familiar with chaos? Okay. So you see, we have this more. X having plus 1 is equal to r x 1 minus n. If we write graph dependence x n plus 1 and x n. For small values, this is, we consider initial conditions on this interval from 0 to 1. So we start with any point. Okay? So new value, xn plus 1, will be this one. Yep. Now, let's draw a diagonal. Okay. This is new value, and this value will be new value of this variable. This is, let's say, x0, and this will be x1. Okay. Then we go to the intersection with again. This will be new value of x. And it is clear that if r is less than 1, then all initial conditions will end up at the origin. Then, but what will happen here? In this case, then we have this situation. Oh, sorry. We go here, then we go here, and we'll finally will converge to this point. If we continue increasing r, then trajectories will start changing periodically. They will converge in period 2 trajectory. They will end up in a state when they, if they stay at certain moment at this point, x. Then the next step will be here, then they go back, and it is called period 2 trajectory. Then with increasing r, the transition period photogen, and so on. And finally, all this ends up in chaos. It means that you cannot predict where a system will go. Actually, you can exactly compute where you will go, but small change in initial conditions will radically change behavior very soon. This is basic notion of chaos. Small change in initial conditions causes unpredictable change in behavior. There is another term called to chaos, which is butterfly effect. So the thing is that equations that govern weather, they also non-linear equations, and they have chaotic solutions. And somebody stated that the result can be the following. Flaps of a butterfly somewhere in Brazil may trigger tornado somewhere in Texas. So this is also something that is employed before our talk. Now, this was chaos in one dimension. Now, if we have two dimensions, if we have a system which can be described not only by coordinates, but also by speed, in mechanics, very simple one-dimensional motion in physics. If you know initial position, you still don't have all information about the system. You need to know velocity of this system, the initial. The set of variables that describe this kind of systems consists of position and velocity. If you know position and velocity, you know action. Now, this kind of systems can be described by position on in space and x. So if we are originally were somewhere here, then next will go here, 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 and where and regular solutions are most systematically behave when there is no strong nonlinearity. With appearance of nonlinearity, systems become again chaotic, but they have regular solution behavior demonstrate simultaneously. Regular behavior, this is regular behavior, and chaotic behavior, depending on the initial condition. This is how nonlinear systems behave. Now, why am I talking about this? Because it turns out that almost all systems have power or memory in certain sense. Because we talked about the result yes, we know that almost all systems are non-linear. Yes? Linearity is just approximation. Now, when nonlinearity is strong enough, there is chaos. And there are areas of regular motion and areas of chaotic motion. But when a system is in chaotic sheet, is called chaotic sheet, it may appear near area of regular motion, and when it appears near the area of regular motion, it stays here, it may stay quite long. And actually time of staying near the area of regular motion is proportional to the area of this island. So it may stay certain time near this island, so then it may stay long, actually inversely proportional. It will stay longer near this island and so on.
When you say this island, it's inversely proportional to the size of the small college, right? Like the ones on the outside, that's what you're referring to, right?
Okay, those are consecutive zooms. This is first zoom, then within this island, sorry, this island, right here. Okay? Now, areas of consecutive islands, if we go deeper into it decreases. Those areas, but those are areas of regular motion. They correspond to periodic trajectories in one-dimensional case. Here it's period 3, here it's 8, period 8, and so on. I don't want to go deeper. But I want to make statements that all systems have power-law memory. This is why I am staying here. You have a set of Newton equations. System is not linear, and it demonstrates behavior of power law. Why? Because there's a character of time which this chaotic system span near islands, and this creates situation, such a situation, the diffusion in nonlinear systems can be described by fractional differential equations. So system effectively, all nonlinear systems, they effectively have power law memory. And that they remember that they stayed somewhere near island. So now everything in the world almost has power law memory. This is example of evolution of such system. You see, it doesn't spread uniformly. It stays for some time near. You see, then it jumps, then again it stays, jumps. And, the result is non-linear process with memory. Diffusion is memory. Now, so we define, we actually already know that this is the simplest form of a map with memory. Now, I want to do something with you. Mathematicians, we came here and we need to have something that we can do together, something simple. So we have this map, and let's consider it for the simplest case when alpha is equal to 1. Okay. Then we have xn is total k equals to 0 to n minus 1, and in this case we have n minus k to 0 power. So it's 1. G, and I mean, for now, H and K are not important. It's G and X. I think when we need it, we'll get. We have this map with memory, and when coefficients are 1, it is called map full map. Full memory. But we can also write x and minus 1 is equal to k 0 to n minus